Hi everybody, so this is the key for quiz 2 for linear algebra for the summer. So the first question asks us to find the ERO matrices describing the relationship between the new rows and the old rows for these steps of Gaussian elimination. So I heard from some people that they were a little tripped up by the fact that there were a couple of row swaps here. So we move 4 up to row 1, and we move row 2 down to row 3, and row 1 we move to row 2. So remember, one thing you can always do, which I think makes it easier, is you can write down these equations. So the new row 1 is the old row 3. The new row 2 is the old row 1. And the new row 3 is the old row 2. Okay, so I like to do this because then the relationship between the old row vector and the new row vector, which gives me this matrix, I can kind of see what it has to be. So if I want in the new, so I'm going to write this as row 1 prime, row 2 prime, row 3 prime, and it's going to be some matrix times the old row vector, row 2, row 3. Okay, so in the first entry, first row, I want to get just row 3. So I'm going to have 0, 0, and then a 1 in the third spot. So for this row 2, if I want row 1, I just put a 1 in the first spot. And then row 3, if I want to get row 2, I'm just going to put a 1 in the middle spot here. So that tells me my first row, first ERO matrix is going to be 0, 0, 1, 1, 0, 0, 0, 1, 0. Okay, so again, I'm going to go through the same thing. So notice on this one, the new row 1 is exactly the old row 1. The new row 2 is going to be the old row 2 minus, so notice we subtract 2 times row 3. And then row 3 is exactly the same. New row 3 is old row 3. Okay, so now just writing out these vector equations, row 1, row 2, row 3, all new, are equal to some matrix times row 1, row 2, row 3. Okay, so I want to get row 1, so I'm going to pick up 1, 0, 0, so 1 times row 1 plus 0 times row 2 plus 0 times row 3. And the second one should be row 2 minus 2 row 3. So it's going to be 0, 1 times row 2 minus 2 times row 3. That's going to be row 2. Now row 3 should be just row 3, which is 0, 0, 1. Okay, so now we get the matrix 1, 0, 0, 0, 1, negative 2, and 0, 0, 1. And then finally, on this last step, row 1 prime is just 1/4 of old row 1. New row 2 is just negative of old row 2. And row 3 is just 1/3 of old row 3. So row 1, row 2, row 3. The new vector is the old vector with the multiplied by the matrix, which is 1/4, 0, 0, 0, negative 1, 0, 0, 0, 1/3. So our matrix is 1/4, 0, 0, 0, negative 1, 0, 0, 0, 1/3. Okay, so now it says write the inverse of the matrix A as the correct product of the ERO matrices E1, E2, and E3. You don't need to actually multiply them out. Okay, so one thing to note here is that I have I'm saying A inverse. So what matrix, when I multiply it by A, gives me back the identity? Well, it's exactly the matrices that are, that is the product of these 3 matrices. These 3 matrices, when I multiplied them one by my original matrix, I ended up with the identity matrix. So the first matrix I multiplied times my original matrix was this one. So the one that would be furthest in or closest to the matrix when we multiply it would be this first one, 0, 0, 1, 1, 0, 0, 0, 1, 0. Then the second one that we applied was this one, 1, 0, 0, 0, 1, negative 2, 0, 0, 1. And then the third one that we applied was this diagonal matrix, 1, 4, 0, 0, 0, negative 1, 0, 0, 0, 1 third. Okay, so this is the product E3, E2, E1. This matrix, it's important that we did the products in this way, otherwise we aren't getting the inverse. Now some people made the mistake of writing down A as the fourth entry here. The inverse won't have A in the product. What you're thinking of is the fact that A inverse times A is the identity. So A inverse we know is E3, E2, E1. So A inverse A is E3, E2, E1, A, which is equal to the identity. But the inverse matrix itself doesn't include A. A is sitting right here. We apply the inverse matrix, which is just this product E3, E2, E1 times A to get the identity. But the inverse matrix is just E3, E2, E1 in this case, or however many ERO matrices you produce in the correct ordering. Now one thing you could always do is actually multiply these matrices out and then multiply that matrix times your original matrix. Now the reason to do that is that if you end up with the identity, chances are you found the inverse correctly, which would mean you did all of the steps correctly. So on an exam, if you have a couple of extra minutes, it's very worth your time to actually multiply these matrices out and check that when you multiply times your original matrix, you do get the identity. Okay, for the following matrices, answer if the matrix A is invertible, and if it is, write the inverse matrix A inverse. If it is not invertible, explain how you know it is not. Okay, so first of all, this matrix is not invertible. Invertible, since it is not square. I think we said that a lot in class. If a matrix is not square, it is not invertible. Okay, the second one is in fact invertible, so I gave you a way of checking if something was invertible in class today. You don't actually have to use that. What we did on Monday was sufficient. But so in class today I said that if AD minus BC is not equal to 0, then this is invertible. In this case, AD minus BC is equal to 4 minus 6, which is negative 2, and it's not 0, so A is invertible. However, like I said, you didn't have to pick up this fact in class to be able to do this problem. The other way we decided something was invertible is by looking at this augmented matrix A bar identity, and we row reduce until we get the identity on the left-hand side. If we can get the identity on the left-hand side without anything breaking down, that means that this matrix was invertible, and what's sitting on the right-hand side is the inverse. So let's go ahead and do Gaussian elimination. So I'm going to leave the first row, 1, 2, 1, 0. Now the second one I'm going to take minus 3 times the first row. So 3 minus 3 is 0. 4 minus 6 is negative 2. 0 minus 3 is minus 3. And then 1 minus 0 is 1. Okay, now I'm going to take the first row and I'm going to add the second row to it. So I get 1, 0, negative 2, 1. And then I'm left with the 0, negative 2, negative 3, 1. Okay, let's do one more. So we'll just multiply the second row by negative 1/2. So we get 1, 0, negative 2, 1, 0, 1, 3/2, negative 1/2. Okay, so that means that this is invertible. So if we can get the identity matrix on the left-hand side, that means this original matrix was invertible. It is indeed invertible. And the inverse matrix is what's sitting on the right-hand side here at the end. So A inverse is negative 2, 1, 3/2, negative 1/2. Now there's a very easy way to check that you did all of this correctly, and that your answer is correct, and all you have to do is multiply your matrix, your inverse matrix, by your original matrix and check that you get the identity. Again, this is a very useful fact that you can check your answer so easily, and I very strongly suggest you do it. If you on an exam aren't checking your answer, if you have time, well, that's not a good sign. That if you make mistakes, I'm not going to be very happy. So, okay, so let's just check. We get -2 plus 3 is 1. -4 plus 4 is 0. 3 halves minus 3 halves is 0. 6 halves, or 3 minus 2, is 1. So we do get the identity, so we found our inverse correctly. Okay, this third problem asks you to interpret the possible solution sets to a system of equations given properties of the original matrix A. So suppose A is a square 3 by 3 matrix, and consider the system of equations AX equal to B. For each of the two following properties of A, select all of the possible descriptions of the solution set for the system of equations AX equals to B. Okay, so if A is invertible, that means that if I write down A bar B, I will eventually, one of the definitions of A being invertible was that when we do row reduction on this augmented matrix, we can get to the identity with some solution over here, which I'm going to call V. Okay, so notice that tells us that exactly our solution set is just the point, right? If we have a 3 by 3 matrix and we end up with ones on the diagonal, then our solution is exactly just this point. Okay, so when A is invertible, the only thing that can happen here is problem 2. Now, for part B, we're just going to kind of think about if A is not invertible, or in other words, we can't get to the identity, are all of the other possibilities valid? So first of all, if we can't get to the identity, we can't get to a situation in which there's only one solution. Okay, so 2 can't happen. We can't have just a point if A is non-invertible. Now we could have no solution. A possibility when we're doing our row reduction is that we'll get to some situation where we have, I don't know, something where we have all zeros in one of the rows on the left-hand side, and we have something that's non-zero on the right-hand side. So that is a possibility. So no solution is a possibility. A line is a possibility. So if we think about this example, if V3 here is 0, then we would have exactly a line solution. So 3 is an option. A plane is also an option, so that would be maybe 1, 0, 0, V1, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so a plane is also a solution. Also, three-dimensional space is a solution, is a possibility. So the other possibility is that we have this augmented matrix. So the matrix of all zeros is not invertible. There's no way to somehow get the identity on the left-hand side after doing row reduction, because no matter how hard we work, we're never going to introduce ones here on the diagonal. It's not possible if all we have to work with is zeros. So this matrix is not invertible, and the solution is three-dimensional space. So this is also a possibility. So if A is invertible, there can only be a point solution, provided that A is square. Well, and it has to be since it's invertible. And if A is non-invertible, so we have all of these different possibilities because maybe A, first of all, isn't square, but given that I said it was square, we can still form these augmented matrices that tell us that we could have the possibility of no solution, a line, a plane, or all of three-dimensional space. Okay, the last problem asks us to think a little bit about vector spaces. So a line in R2 that does not contain the origin 0, 0 is not a vector space. For example, consider the line, which is the set of all points that are on this line, x plus 2y equals 5. Okay, so one thing to note is that my set that I'm thinking about, it's not a vector space, right? But the set that we're considering is the set of all points x, y, such that x plus 2y equals 5. So the set here is the set of points that are on this line. Some people made the mistake of thinking that the set was all lines that don't contain the origin, but no, I told you it's a line in R2 that does not contain the origin, meaning that the elements of the set are the points themselves that are on that line. Okay, so now we kind of know what elements of our set look like. They're points that are on this line. We know what vector addition is because if we're adding 2 points, we just add the vectors like we normally do. We add the x components, we add the y components, and we get a new point. Scalar multiplication, we know what we do. We just multiply each component of our vector. Okay, so now we know what v is, we know what vector addition is, and we know what scalar multiplication is. So the steps when you were thinking about these problems, these vector space problems, the first thing you should always do is identify v. So whether or not it's a vector space, there's always going to be a set you're considering. Make sure you thoroughly understand what the set that you should be thinking about is. So you should be able to describe arbitrary elements of your set. The second thing you should do is identify what the vector addition that we're thinking of is. So here it's not hard because we just have elements of R2. But for example, when we had polynomials of degree 2 or less, figuring out what vector addition was required us to think about how to add 2 polynomials together. We should identify what scalar multiplication means in this situation. So again, for this one, it's not difficult because it's just our normal scalar multiplication on 2 vectors. And then once we have these three things done, one thing I think is always useful is to write down several arbitrary elements in V. Okay, so an arbitrary element in V would just be some point xy that satisfies this equation. Okay, so we know that this is not a vector space, which means it must not satisfy at least one of these requirements for a vector space. So now I'm just going to ask you sort of a few of them to see if we can identify some that aren't satisfied. Maybe there are some that are still satisfied. That won't matter, right? We just need at least one of them to be violated in order to say that this is not a vector space. Okay, so my first question is, does such a line satisfy the additive commutativity property? So remember, I tell you a specific line. I say we have this line without origin, and our elements in that set are points on the line. So when I say, does this satisfy additive commutativity, what I mean is, if I add 2 points on the line, and then I add them in the opposite direction, do I still get the same thing? So u and v here are points on the line. So that's going to obviously be true because whenever I add points in R2, well, I always get I get additive commutativity. Okay, that's a property that this set inherits from R2. So even though this sum might not be in my vector space or in my set V, so excuse me, it's not a vector space, even though this u plus v might not be in my set V, it doesn't matter what order I add these two things, I still get the same elements. We just don't know whether they're in V. So yes, it satisfies additive commutativity because when I take 2 elements, I add them together, this is the same as x2, y2 plus x1, y1. You can add those in any direction in any order, and it doesn't matter. So it is additively commutative. So then the second question says, does such a line satisfy the additive closure property? Now here is where we have to actually check and see if this satisfies this property. So it's not going to satisfy this property. And let's look at our picture, right? If I pick some vector here, so point on my line, and I pick some other point on my line, and I add those 2 points together, okay, no matter which direction I add them, I get this same point up here. So no matter which direction I add, this is additive commutativity, I come to the same point. But additive closure doesn't hold because their sum, this point, is not on the line. Okay, so no. And to explain that to me, you might look at our particular line, pick 2 points on it, add them together, and then show that they're not on our line, so that they don't satisfy this linear equation. So for example, the point 5, 0 is on our line, and the point 0, 5 halves, those are both on our line. They're both in V. But then when we add them together, we get 5, 5 halves, which is not on our line. It's not in the set V, since 5 plus 2 times 5 halves, so I'm just plugging it into my equation which describes my line, is not equal to 5. This value is 10. Okay? So our line does not satisfy additive closure because if I can find an example, a line, which is an example of my, V description, which I pick 2 points on it and then I add those points together and I see that I have a point that's not on the line. So it's not closed under addition. And then does such a line satisfy the multiplicative closure property? Again, this is no. So in the picture, this we might be looking, here's our one of our vectors. Now if I multiply this vector by any scalar, for example 2, I get a point that's not on my line. Okay, and so we might pick the example 5, 0. So no, 5, 0 is in V. But when I multiply this times 2, I get 10, 0, which is not in V. Since when I plug in the values x and y into our linear equation, they're not satisfied. These points are not on this line. So 10 is not equal to 5.